Welcome back to the Foundations of Calculus. Today I'm going to help you master derivatives of polynomial and exponential functions. Before we dive right into examples in theory though, I always like to go over the why. Why are we doing this? Why do we care? So you can see here I have a badly drawn rocket ship, and let's say we want to find the speed it was going in the air, at least in Earth's atmosphere. So right off the bat, not the easiest thing to find, but with a little bit of calculus, we can find it out. So the height of our rocket ship can actually be given by this equation. So negative 4.9 times time squared, and negative 4.9, that's just half the acceleration of Earth's gravity, times time squared, plus the initial velocity times time, plus the initial height. So I'm not going to go over how this equation was derived, just assume this equation's correct. But from this equation, we can find the velocity at any time t. And we can do that by taking the derivative. So I'll go much more into depth on how I'm actually taking this derivative. But just to show you, this is how we can find velocity from the above equation. So if you want to find the speed at any point in the Earth's atmosphere at any time t, you would just find it this way. So that's kind of a real world example of why this is useful, how this can be used. So let's go much more into detail on how to find it. So how did I actually find that derivative? Well, that was a polynomial function, and there's a rule when we're taking the derivative of a polynomial, or anything to the power. It is called the power rule, and we can write this. So let's say we have a function f of x, which is x to the n. And let's say we have a constant out front. So the a can be any real number, x is the variable, and n up here can be any real number. If we want to take the derivative, so if I wanted to take d by dx, which this is just saying the derivative with respect to x is our variable, of f of x, which can also be written as f prime of x. That prime just means that, think of it like this d by dx. You're just taking the derivative of f of x. This equals, so if we want to take the derivative of a polynomial equation, we would so we could bring the constant out front. So let's take that constant out front. And then we can actually derive this. So we could write this as d by dx of x to the n. You'll notice that the constant we just skipped, and we can then write this as a times n. So what we do is we bring the exponent down from the variable, and then we minus that exponent by 1. So given another example, let's put some numbers to this. Let's say this is 7x to the 4. If we want to take the derivative of this, this would be 7 times 4 x, and then 4 minus 1 is 3, which simplified, that is 28x to the 3. And that's all the power rule is. Let's say we had a constant though. So if we had f of x equals, or I'll use a different function, h of x equals 3, we can write this as 3x to the 0, because x to the 0 is just 1. And if we take the derivative of this, we know the 0 comes down, and then that multiplies by 3x. 0 minus 1 is just that to the negative 1. But because it's times by 0, just equal to 0. So the derivative of a constant is just 0. However, if we have a constant out front of the variable, we can derive just the variable itself. Same thing as we did here, just to show kind of how that was written out. And then this is just for one variable. What if we had an actual equation? So from before, as I mentioned, we might have a function separated by pluses or minuses as well. And given this, we can use what's called the sum or the difference rules. So all that is, if we wanted to take the derivative of f of x, all we could do, or all we'd have to do, is distribute the derivative to each of these. So in actuality, we're taking the derivative of x1, the derivative of x2, all the way to xn separately. So, and that is whether you have a plus or a minus. So let's say you had a x squared plus an x minus an x cubed. So let's say this is h of x, and we want to take the derivative of h of x. So all we could do is, or all we would need to do is take the derivative separately. So let's start with x squared. As we know before, we take the exponent and drop it down in front, minus the 2 by 1. So this is 2x to the 1, plus x to the nothing is x to the 1. You just don't need to write the 1. So you bring the 1 down, and x becomes x1 minus 0, which is 1. So this is just plus 1. Minus x to the 3, again, bring the 3 down. X squared, 3 minus 1. So we can take the derivative of each term separately. One important function that I do want to bring up, though, and an important rule, is the natural exponential base, e to the x. Now, e to the x is very special. The derivative of e to the x is itself. Oh. So the derivative of e to the x equals e to the x. It is not x e to the x minus 1. It is not this as it was before. This is a very special function, as it is the natural exponential base, but yeah, it does not follow the power rule. Okay, so we've gone over a lot of theory, including the power rule, summation rule, difference rules. We've gone over a real world example to give a little motivation of why. Now it's time for a few examples. I strongly recommend that you pause the video between each example and try the problem, or at least attempt it. If you are struggling on an area of the problem, make a note of where you struggled and why. Was it you didn't remember the rule? Was it you did it too quick, wrong derivation? Once you recognize where you went wrong, try to make a little sheet of how to correct that. So for example, if you forgot the rule, maybe try a few more examples on your own and strengthen it up there. But yeah, let's jump into a few examples. Okay, so our first example, the function f of y equals a over y to the 5. That's a bad plus, but plus b e to the y. So let's rewrite this a little bit first so it's a little bit more familiar. So we have a constant a times y to the negative 5 plus b e to the y. Now, three rules we have to use right away. So first, we see that this is, we have a polynomial equation and an exponential function separated by a plus. So to take the derivative of this, we can take the derivative of each separately. So we have to use the summation rule. Also, the e to the y, remember from before, the derivative of e to the x, x being y in this case, is e to the y. So let's break this down. A y to the negative 5, we bring that negative 5 out front. It now is being times or multiplied by the a, but we don't know what a is. So that's negative 5 times a. Y to the negative 5 minus 1 is minus 6, plus b to the e to the y. Nothing gets brought out, so it's just b e to the y. If we wanted to write this as before as well, we could simplify it further by minus 5a over y to the 6 plus b times e to the y. And that's the answer for our first problem. Okay, so for our next problem, we have f of r equals e to the r plus r to the e plus a to the e. Now this one might look a little bit more confusing at first, and it does ramp up in really understanding what is going on, which is why I wanted to include it, but it's actually not that difficult. So let's break this down step by step. So when you see a problem like this, if at first you're unsure of what's even going on, it's really good to see what's going on, or it's really good to see kind of take a step back. So we have a equation separated by pluses. So we know that we're going to take the derivative of each individually. Next, we know we have an e to the r, where that r is what we're differentiating by. So this is just itself. So let me actually write that. So that is just e to the r. Next, we have r to the e. Now r is our variable, and e right now is e to the 1. That's just a number. So you can rewrite this, if it makes it easier, as almost x to the a. That's all that is. So we bring the e down. So that's e times r to the e minus 1, because we always minus it by 1. Next, a to the e. A is a constant in this case. It's not a variable that we are differentiating by. And it's to the e. This is just 0. So the derivative, and the derivative is often denoted with this little prime. This represents how many derivatives were taken. So let's actually take a second derivative. So we're going to derive our equation twice. Well, it's the exact same thing as before. We have our equation separated by pluses, so we know we have to take the derivative of each individually. So we have that e to the r again, which is simply just e to the r. And then we have the same thing, so we take that e minus 1 down, e minus 1, multiplied by the e, and then this is the power rule again, so we just minus this by 1. And then you could keep going if you wanted. You could go to 3, 4, 5, 6th derivative if you wanted. But right now, this is the answer to what is the second derivative. So next up, we have f of x equals the square root of x plus x cubed over x squared. Now at first, it might seem like we can't use any of the rules we've talked about before, but we can if we do a little bit of simplification. So x squared can be rewritten. Oh, that has a really bad x. Is x to the 1/2 over x squared, and we can break this up by the plus. So that is x cubed over x squared. Now this is starting to look a little bit more like something we can work with, but we have one more step. So anytime you divide two variables, it is the same thing as saying x to 1/2 minus 2. So rewritten, minus 2 can also be rewritten as 4 over 2, just so we have common denominators. And then this is x 3 minus 2. So simplified, this is x to the negative 3 over 2 plus x to the 1. And now we can use the power rule. So from before, if we bring the 3 down, the 3 over 2 down, that's negative 3 over 2 times x minus 3 over 2 minus 1 is minus 3 over 2 minus 2 over 2 for the common denominator, which equals minus 5 over 2, plus x to the 1 is just 1. And if you take that 1, minus that 1 by 0, so that is x to the 0, which is just 1. So you can just write 1 in that case. And then yeah, that is our answer for this one. And yeah, that's about it. Good job for making it to the end of the video. Leave a like and subscribe if it helped, and a comment if you'd like to see anything else.